Hello again. Today we're doing another problem from the Landau Lifshitz mechanics chapter, doing problem 3, in which we have a simple pendulum with a support that will be moving in a variety of paths. The first path that we'll be considering is that the support moves uniformly in a circle that is vertical. Second path will be similar, except that the point will be oscillating back and forth horizontally with a frequency that matches the motion from part A, but that is just moving horizontally, not vertically. And lastly, we'll be considering motion where the support is moving vertically with the same frequency with no horizontal motion. For this problem, I'm going to start by defining all of the coordinates and the coordinate transformations, and then we'll move on from there. So we're using x, y, x prime, and y prime, or equivalently, just one angle phi and its time derivative. These coordinates will be applicable to each of the cases above, and we'll only need to plug in the specific motion of the support for each of those individual cases. Now we can express the kinetic energy in terms first of the Cartesian coordinates and next using those Cartesian coordinates plugged into our coordinate transformations so that they're expressed in terms of the support position, x naught and y naught, along with the angle and its time derivative. Potential energy is also fairly straightforward. It's negative mgy, because the coordinate system we're using picks the y-axis pointing downwards, and then we plug in given values for y based on our coordinate transformations. And now we're ready to combine these and create the Lagrangian. Now that we have the Lagrangian, we can, for each of the cases, express the position of the support with respect to time. In the first case, the support is moving in a circle, so the x and the y axes, the x and the y components, are cosine and sine of the angle gamma t. And we can also calculate their time derivatives. And this will allow us to fully express our Lagrangian. Now we can start simplifying the Lagrangian by removing any constant terms. So a squared gamma squared is a constant. And we can start simplifying using trigonometric identities. In this case, combining the sine and cosine terms. And we are going to use this trick in order to eliminate the phi prime, phi dot, from our Lagrangian, or one of the terms of our Lagrangian, utilizing the fact that the Lagrangian is not changed if we add an overall derivative with respect to time. So if we take the derivative of cosine of gamma t plus phi with respect to time, that splits into these two terms using the product rule. And we see that one of those terms is present in our Lagrangian, which means that it can actually be swapped out for the other term in that product. And that's how the phi dot becomes a gamma. And the sign flips. This a sine gamma t is also an overall derivative with respect to time, so it can be eliminated as well. Starting the next case, now we're looking at vertically, or rather a horizontally oscillating support, which is slightly simpler than the case above, because now we only have x naught, y naught, and y naught dot are both 0. So we can immediately start with our Lagrangian from the circular rotating case and delete the terms corresponding to y naught. Now we can plug in for x naught. And again, we can use a similar trick in order to eliminate phi dot. So we take the total time derivative of sine gamma t times sine phi, get two terms, one of which matches the term in our Lagrangian, and the other is similar, except with a gamma and different trigonometric functions. Lastly, we'll be doing the third case, which is very similar to the first two, especially the second, except now it'll be y naught that is oscillating instead of x naught. The trick that we use to simplify this Lagrangian, or this term from this Lagrangian, is almost identical to the one used in the previous part. And the goal is to remove phi dot and replace it with gamma, because gamma is a constant, which if we were going to solve the actual equations of motion for this Lagrangian, would be easy to deal with, whereas phi dot would require an actual partial derivative or total derivative, depending on which part of the equations in motion we're evaluating. And now we're just about at the end of this problem. So I'll be back again soon for the next problem as I work on adding voiceovers to my earlier videos.